So here we go. So let's talk about orienting a surface. So you guys learned about parameterizing surfaces. So orienting a surface. On each point of a surface, there are two directions normal to the surface. Okay? So a surface is orientable if one normal at each point can be picked in a continuous way. So what does that mean? That just means the surface has two distinct sides. Right? Given any point on the surface, you could point normal in one way or the other, and that would create two distinct sides to the surface. Make sure your brain is 100% on and you're not just writing, okay? You can always take good notes later from the video. So orientable surface means that you can one normal at each point can be picked in a continuous way, and that the easy way to think of that is it has two sides. So the direction of the so then we have to pick which way is the direction of positive, and then we're going to call that n, right? So for any given point, there's two normal vectors, one on each side. Then you have to pick one side and say that's the direction of positive, and we'll call that n. All right, so here's an example, right? So here's a surface. And so what I'm picking as the orientation is generally up here. Do you see that? So my vectors n are generally pointing up. So that's the orientation of the surface. I could have picked generally down. That would be the opposite direction of all those vectors, and then we'd be orienting the surface generally down. That make sense? Okay, that's called an open surface. All right, an open surface has a boundary C that will distinguish the two sides. So do you see that there's a boundary around this? So I could call the boundary C. If it has a boundary like a closed curve that separates the two sides, that's called an open surface. And in this case, normally like either plus or minus x, plus or minus y, or plus x, plus y, or plus z would be chosen as orientation. So like in this case, we might choose plus c. That's what I'm showing anyway. I'm showing a positive orientation of plus c. Plus z, upward. All right, another kind of surface that's orientable is called a closed surface. So closed surfaces have an inside and an outside. And typically, pointing out is positive orientation. That's what I'm showing there in that picture. So here I've got like a paraboloid and like a disc making a closed surface. And so you've got the two sides. You've got the outside and the inside. And I'm showing outward as positive orientation. So the direction of the vectors n is pointing out from inside out. And again, those vectors are all orthogonal to the surface at every point. So these are the two basic types of orientable surfaces: open surfaces and closed surfaces. So what about a non-orientable surface? What's a non-orientable surface? It's kind of like it's a surface but doesn't actually have two sides. So you know what the example of that is? So like a Mobius strip. So watch what happens here. If I start at this point P, and then I start continuously drawing the orthogonal vectors, so now they're like down, right? So then they're down and kind of behind there, and then they're coming this way, and now they're up here. See that? And now they're up and at us, and now they're to the, look what happens. Now they're to the right, I come back, what happens? I get back to P, and my orthogonal vector is pointing the other way because I'm on the same side of the surface that I started on, but now at that point P, I've got vectors in both directions. See that? So a Mobius strip, it doesn't really have two sides, it just has one side. And because of that, you can't pick an orientation that works, right? I picked n to be this way, and then I worked my way around, and I'm still in the direction of n, but now it's the opposite way of n. See that? So that's the example of a surface that is not orientable. And it's the last one we'll see this semester. You only have to worry about open and closed surfaces, which are orientable. Okay, does this slide make sense? Ask me if I lost you. Yes, please.
When it says that a point can be picked in a continuous way, what does that mean?
Well, that's kind of what I just did here. So I was picking these vectors. I started n here, and if I went in a continuous way, drawing ends that are consistent with that one, when I came around, then it was the opposite.
You should wind up back in the spot.
I should, when I make it back here, I should have the exact same one that I started with, but I got the opposite one.
Okay.
So I cannot pick a direction, an orientation in a continuous way, because when I came around, I got the opposite. These can all, so once you're on one side and you move around, it'll consistently point the one way, and when you're on the other side of the surface, you move around, it'll all point the other way. Does that make sense?
Yeah.
Okay. Other questions? Okay. So that's what orienting a surface is about. Okay, so we're going to talk about flux. It's getting good now. Flux. All right, so we'll start simple. So before we get to flux, we have to talk about what an area vector is. So area vectors have two things. What do they have? All vectors have? Magnitude and direction. Okay, so an area vector, we use capital S vector to denote an area vector. And so what do you suppose the magnitude of an area vector is? Area of a region, right? And then what about the direction of an area vector? It'd be orthogonal, right? So if you had some surface, in terms of orienting that region, you would want the vector orthogonal would orient it, just like the orthogonal vector oriented a plane. Remember that? The vector that we chose that was the orientation of a plane in space was orthogonal to it. Same thing. Okay, so here's a real simple example. A 5x3 horizontal surface in R3 oriented upwards. What would the area vector be? So think magnitude and direction here. Magnitude and direction. So what would that area vector be? It's a vector whose magnitude is the area and whose direction is orthogonal in the direction of the orientation. So what vector has its magnitude as the area of the surface, and then is orthogonal to the surface? What would this one be? Yeah. 0, 0, 15. Yes, 0, 0, 15, right? Or 15K, right? 15K. He said 0, 0, 15. That's the same thing, right? Make sense? Okay, so what is flux? Flux is the rate of flow of some field through S. So you can imagine like a membrane in a fluid, right? And so there's flow, there's the fluid flow. So what's the rate of flow of that fluid through the membrane? Like air through a screen or something like this. You'd have your vector field F would be like a wind field or something, and then your S would be like a screen, and you're talking about at that screen, what is the rate of flow of the air through the screen? Those are just examples. Okay, so if I had this, suppose I'm looking at this one here. Suppose here is my vector field at all these different points on my surface, right? So all I care about is the vectors on the surface, and I want the flux. Then what component of those vectors do I want? Do I want the components parallel to S or perpendicular to S? Do I want the components of these vectors? Well, okay, so there's the surface and there's S. I'm asking about S. Do I want I want it to be perpendicular to the surface. Therefore, I want the components that are parallel to S, right? The components of those vectors that are orthogonal to S are in parallel to the plane. So you wouldn't have any flow in that direction. Do you see that? So I want the flow, when I'm measuring flow, I'm I want the part that's perpendicular to your surface, which would be parallel to S because S is perpendicular to the surface, right? So therefore, is flux a matter of dot product or cross product? We want as much of F as in the direction of S. Remember, and that's our dot product, right? So I want F dot S. I want as much of my force or my vector field vectors as it parallel to S so that that's perpendicular to the surface. So that's the general formula, F dot S. Okay, so if the net flow through a surface the net flow, if you take the consideration over the whole surface and you get a net result in the direction of n, then you have positive flux. So that's why we need to orient the surface so we know like which way is the direction of positive flow or which way is the direction of negative flow. Okay, so here's an example. Water flows at 3 centimeters per second through a circular pipe with a radius of 2. Find the flux through the elliptical region, which is angled at theta radians to the flow. Okay, so we got 3 centimeters per second here. Black. And then here's my Here's my S vector here. And that's angled at theta to the direction of flow. Okay, so how do we calculate flux? F dot S. And what's the easy way to get a dot product? Magnitude of each times. Now cosine of theta, which is the angle between the two. Okay, so this is how we're going to do it. So what is F? What is my F? So that's the magnitude of my vector field. What would that be? That's just 3, right? 3 centimeters per second. Okay, and then what about the magnitude of S? Okay, so the magnitude of S means what? The area of this. Oh, uh-oh, we got an ellipse, right? We actually got a kind of an easy way to do this. So we need that light blue area there. So what we can do is we can make like a right triangle with a circle that's orthogonal to the flow, and we can use like triangle trig, but with areas. Does that make sense? So this ends up being this angle between my disk and my ellipse is actually theta. It's the same angle as this. So what's the relationship? The area of the circle equals? So that's like what? That's like the adjacent side of the triangle, right? So the area of the circle equals? It's going to be my area of my hypotenuse times cosine theta, right? So it's like adjacent equals hypotenuse. Cosine is adjacent over hypotenuse. So I'm just using triangle trig here, but instead of the length of the sides, I'm using areas. Do you follow it? Yeah. And what's the area of the circle? Pi times 2 squared, right? The radius is, so I know the area of the circle. So the area of my surface, my magnitude of my S vector, is just going to be pi times 2 squared over cosine theta, right? What happens? See the cosines go away. And the point, so what's the point of that is, so what do we got? 3 pi, 12 pi. And the units on that will be centimeter cubed per second. So flow rate, right? Volume per second. So what's the significance of the fact that the cosine theta went away? What does that tell us about this problem? The flux, what? Yeah, it doesn't matter how that surface is tilted. Doesn't matter what that theta is. You have the same flow through the pipe, right? And that's just the flow through the angled surface will be the same because of this thing of what? It's always it's always going to be the horizontal component that you're summing up. In this case, horizontal is the direction of flow. Okay, does that example kind of help with a simple flux problem? The ones we do are going to be a lot more complicated. Starting simple. Oh yeah. Trust me. We're at the end of Calc 3. It's about to get really bad. You carve out more time than usual. It's about to get hard. Any questions on this? The basics of flux. Okay. So let's do, oh, there we go, I already had all that. Okay, so let's try this example. So now my surface is x equals 1 from 0 to 4 and 0 to 2 through the field y minus 1 comma z comma 0. So what makes this example different now? Why is this a 1 degree harder than previous? Cody knows. What's different about this now? Yeah.
The flow is not constant.
Yeah, so now we got a actual vector function, vector field, where it's different in different places. So let's take a picture of what's happening here. Or let's look at the image of it. So here, it's like a two-dimensional line integral. It's a flux, right? It's through the surface. All right, so I got here we are. Here's my x equals 1 over that boundary, and then I'm in this this vector field. So first of all, what vectors of the vector field do I care about? Which vectors do I care about if I want to know the flux through that surface? The ones at the points of the surface, right? That's all I care about. So let's show those. Okay, so this is a sampling of the vectors that are at the surface itself. Okay, now what component of those vectors do I care about for flux?
The ones in the x direction.
Okay, so yeah, so you could say parallel to S or in the x direction or how related to the surface? Orthogonal to the surface, right? So I only care about, I'm showing in blue now, I'm showing the orthogonal components, the components of those red vectors orthogonal to the surface. Do you see it? Does it make sense? Okay, so all I care about then is these components of the actual vectors at the surface itself. And so what do we predict? If I make the orientation in the positive x direction, then what do I expect for the flux? Positive, right? Because the net amount of flow, there is some flow in the negative direction, but way more flow coming forward. See that? So we're expecting our answer here to be positive. If we make the orientation of the surface in the positive x direction, we expect positive flux. So this is what I just showed you is the idea what's going on when we calculate a flux integral. Does that make sense? Good. Okay, so where are we? So let's draw it here. So x equals 1, y from 0 to 4, d from 0 to 2. That's it right there. Okay, so what is my, I got my field. What is my area vector? What's my area vector? Eight I. Okay, and I'm going to do what? I'm going to dot that with? Is that what I do? I'm just going to go y minus 1, z 0 dot 800. Is that going to work? There's a big problem with that. What's the problem with this? What's that? Why can we not use, exactly, why can we not use an area vector for the whole surface? Yeah.
Because the flux across all the points is constantly changing.
Right, because the field is constantly changing across that surface. As soon as you move, you have a different vector. You can't, so the only way you could use 8I is if you have a constant field for the whole thing, like we did in the previous example. So this is no good. We can't do this. So what do we have to do instead? We have to consider what? A point-wise consideration. So what does that mean? How do we do that? Yeah, so how do we do it at each point? So we're going to do it element by element and let those elements get really small, right? We're going to do element by element and let those elements get real small. So this element consists of what? What is it? Right. So this is dy dz element. Now, I can write an area vector for that. And what will we use for that area vector? ds, right? So rather than an S area vector for the whole thing, I'm going to have a ds for every little spot on that whole surface. So what will ds be? Okay, but it's a vector. So yeah, that's the magnitude of it, right? The magnitude is dy dz, but what's the vector? Right, dy dz, comma, 0, comma, 0. The area is the magnitude is the area of the element, and the direction is what? Orthogonal to the surface. And then I have my f dot z, or sorry, then I have my f, and so now how am I going to get the net flux through that thing? What will this be to get the net flux? Yep, so we're going to now do f dot ds, but then that's only for one of them. How do we get them all?
We bring the integral in.
Yeah, we're going to accumulate, right? We're going to accumulate over the whole surface.
dy dx or dy dz, dz dy for the integral.
Yeah, so no, that'll become part of the dot product. It's already there, right? So what is f? Y minus 1, z 0, and then we do dot, dy dz, 0, 0. So don't erase this on your paper. Keep that on your paper. I just need room. Okay, so what do we get? We get the integral of y minus 1 times. And why does it make sense that we only grab the x component of this vector field?
Because that's the component that's locked.
Right, that was that. Remember when I showed you the actual vectors, and then what did we want? We wanted the vectors orthogonal to the surface only, so we wanted the component in the x direction. So that's why this happens. It just grabs those x components. Y is going to go from what to what? 0 to 4. Z goes from. And we expect what value for this? Let's see, y squared over 2 minus y from 0 to 4. Is it 4? So is it 8? So it's positive, just like we expected. Yeah, please.
So if we have a plane that isn't necessarily in the I, J, or K direction, but we have to find the gradient of the surface. So
We're getting there. We're going to do it for curved surface now. Yeah. That's when it gets tough. But we got to get the underlying ideas here. So starting simpler because we really want to understand what flux is about. F dot S. So now if your F varies over your surface, then we've got to look at DS's. Okay, any questions? So now what's the most general case? That you could have a vector field that's varied like this, and also a surface that's curved, right? This is where it gets tricky. So I've got this curved surface. So I need to what? Look at the surface. Look at every vector from the vector field at every point on the surface. So we're going to have to chop that thing up into elements. But the way that we parameterize the surface might not be, because we're in R, the surface is in R3, it might not be X and Y or Y and Z or X and Z. So like you saw, there's lots of ways to parameterize the surface. And so I'm just generally call it U and V. So U and V may or may not be X, Y, and or Z, maybe something else. But it's like it's a different pair of parameters that aren't necessarily coincide with X, Y, and Z. Okay, so just generically U and V. So to get what do we need? We need the n vector, right? We need the vector that's orthogonal to the surface. That's going to come from the vectors that point in the direction of these contour lines along U and V. Okay, and so those are what? Those are like parallel vectors to these contour lines of U and V. So those will be from the partial derivatives of U and V, right? So if I have my parameterized surface, I take the partial derivative of that surface with respect to U. That's going to give me, just like in our in our vector functions of curves, right? Remember that? And when we had curves in space, how did we get vectors that were in the direction of the curve? How do we get those? If this was R sub t. It was r prime t function, right? Those were the r prime t was the function of vectors that point in the direction of the curve. So now with the same thing here, I need vectors in the direction of the contour lines of u and v. So I'm going to do partial derivatives of my vector function of u and v. So the partial with respect to u is going to give me vectors in the direction of u for a constant v, and my partial with respect to v is going to be vectors in the direction of v for a constant u. Why do I need that? Why do I want that? Because I'm trying to get n, right? Where's n going to come from? So when I do that, when I take the RU and RV vectors, those are actually what? Those will actually create like a little planar element. So I'm showing that pink. Okay, so when I do RU and RV, those are going to make like a little parallelogram. And that parallelogram is like modeling the like curved element. See that? So let's make that bigger. So, okay, so then if I multiplied each of those RU and RV by DU and DV, it'll scale that pink element to match the size of the blue element. Okay, so this RU might be super big like this or super small, and RV might be something else. But in order to get the size of the pink parallelogram to match the blue one, I'm going to multiply by DU and DV. That will scale it to the size of the blue element. Okay, so here's what that looks like. So I've got a parallelogram element trying to replicate the curved blue element. And so what do I want now? I want the area vector. What is the area vector? Its direction is what? Orthogonal. So the direction of the area vector will be orthogonal. And what will its magnitude be? Area of? So I've got these two vectors that form my parallelogram. I want a vector. This is awesome. I want a vector whose magnitude is the area of the parallelogram and whose direction is orthogonal to those two vectors. We have it. What is it? That's exactly what the cross product does. The cross product gives what? It gives the area of the parallelogram, and it also gives a vector orthogonal to it. It's exactly what we need. So awesome, right? So this is in the direction of n. So the cross product of those two vectors, orthogonal to the surface, area of the surface. That's the area vector. So the cross product gives us the area vector. So the du RU cross dv RV, its magnitude is what we call ds. So ds without the vector is just the area. Okay? As a vector, it also is in the direction of n. So this is just the area because I'm taking the magnitude of it. ds is area and in the normal direction.
So have we been using surface area this entire time when doing line integrals, or is it just for flux?
Line integrals, no, we were doing dot product, right? We were dotting f dot dr. So we were accumulating the work along the path. So that's, I mean, this is the analogous situation to line integrals in two dimensions. But it's different in that we were doing f dot dr, and that took us along the curve. Now we need those vectors to be orthogonal to the surface. So that's why we use cross product. So if it doesn't have the vector on it, it's just the area. If it's the ds vector, it's the area, and it has the direction, this direction orthogonal to the surface, the parallelogram, and thus the surface. Okay, so this is a kind of side note then. Now that we have if this is ds, right? So it's the partial with respect to u of your parameterized surface crossed with your partial with respect to v. That gives you a vector function. Take the magnitude of that, du dv, and that's the area. That's a little area of one element. So as a side note, this allows us to find surface area. If we do a double integral of just ds, ds being this, that'll allow us to calculate just the area of a surface. So it's related to, but not the same as flux, okay? So this is related to flux. Where we're summing up all the little area vectors. Each of those area vectors is the cross product of our RU du and RV dv. the magnitude of that. Okay, so now back to flux, So another way to express the point area vector would be take the area vector times n. So what is n? How would we get n out of these, right? How would we get the vector n? It's a unit vector orthogonal. So what do we do? How do we get the orthogonal unit vector to those two sides of the parallelogram? What would we do? I want just n now. I don't want ds, I just want n. What would you do? Yeah.
Take the cross product and divide by the magnitude.
Yeah, so you take the cross product and then divide by the magnitude of that, right? And that would be the n, just the direction. So now if I do the math here, so I'm going to do that. That's my n right there. The cross product divided by the magnitude gives me just n. And then this is what we just calculated above as just the area part. What do we get? So you see that those magnitudes go away. And so our point area vector is just the cross product. Times du dv, right? So that's the du dv. So the cross product du dv is exactly this for flux integral. It's exactly what we need. It is the area of the parallelogram and the direction normal to the surface. So therefore the flux, this is how we calculate the flux. F dot ds, where ds is essentially the cross product of the two vectors that make up that parallelogram. The area is the area of the parallelogram, the direction is n. That's what we want. We want as much of f as is in the direction of n. And that's what that cross product is. Okay, so in all that discussion, we got we got our flux and general flux integral. But then we also, along the way, as a residual, we got a surface area, way to calculate surface area. Okay, if I lost you, please ask. It's the best I got. Hard stuff. Please.
Where is the region R? The we changed from the region S to region R. What is that?
What do you mean R? The region R?
Well, we were integrating over S, and then we changed to over the region R.
Yeah. Okay. So. Okay. Yes. Right. So S is that surface, like in R3, just as its own. But then, when it comes to actually integrating it, it's like we have to transform that into the variables of U and V. So R is like that surface projected into the UV plane. So you get a double integral in the whatever the UV plane is. And that might exist geometrically or not, because if you say U and V were phi and theta, okay, there is no phi theta plane, but that's what that does. That takes the surface that's in R3, and now our double integral is going to be a double integral in the phi v plane. It's like transforming that surface into the plane of those two variables.
Okay.
Does that kind of help?
Yeah.
Yeah. And that may have a geometric representation or not. You might, so maybe the two u and v that you pick are y and r, right? R for radius, like in polar, and y. Well, so then you're doing a double integral in the y-r plane, whatever that is, right? So it's a transformation of your surface in R3 into the realm of the two variables that you're using. Great question. Thank you for pointing that out. Yeah.
In this case, would R be the parallelogram before it's transformed into the actual surface?
No, R is this whole surface in the UV realm or plane, whatever that is. So if u and v were x and y, then it would be the projection of the surface into the xy plane, and you'd be integrating over that surface. If u and v were yz, it would be the projection of that surface into the yz plane, and your double integral would be in the yz plane. So where it gets a little dicey is when you start using the polar and the spherical coordinates and their angles or radius or like rho. So like say r and u and v are rho and phi. Okay, well we just had to just trust that there's the rho phi plane exists and it's the surface being projected into the rho phi plane. You just do the math and try not to hurt yourself thinking about that, right? Okay, that's awesome. I'm so glad you asked that. Thank you. Any other questions? All right, so let's try another example here. This is going to entail parameterizing the surface. And so now we have choices, right? We have choices of what square? Unit square. Okay. So we have choices about how we're going to parameterize the surface, right? We've got to parameterize it into some variables u and v, like you did yesterday. Now we need to do that. So z equals 4 minus x squared minus y squared, there's actually two parameterizations, right? What are the two, or the natural, right? There's two natural parameterizations of that. What would they be? What would the two natural parameterizations of that be for u and v? So like what's that? Yeah, we're going to say x and y. So then you have to say like r, x, y, and then? Yeah. Polar, right? So like r and theta. So which is going to be more natural for this flux problem? XY or r theta? What? And someone just started saying XY. How come? What does it have to do with? What this choice has to do with what? Does it have to do with the field? It has to do with what part of this, so it has to do with what part of this we're taking, right? And what part of this are we taking? Unit square in the xy plane. So how do we want to work with that? Do we want to work with x and y or r and theta? R and theta, have fun, right? A vertical line and a horizontal line in the polar plane. And then it'd have to be done piecewise, right? You'd have angles up to there, right? Would be according to this vertical line, and then angles from whatever pi over 4 to pi over 2 would be according to this horizontal line. Vertical and horizontal lines are not so, polar friendly. But what about x and y? Super easy, right? Unit square and x and y is like the easiest possible way you could have, easiest possible thing you could have, right? So let's do it. Here we go. So we want to do integral of f dot ds. What did we say that was? F dot RU cross RV dA. And what is our u and v? X and y. So we're going to parameterize that surface as x and y, and then we're going to take the partial with respect to x and the partial with respect to y. And we're going to take the cross product. And then we're going to go, y is going to go from 0 to 1, 0 to 1. So this surface flux integral, really what happens is it gets transformed into a standard double integral. Once we get all the vectors out, eventually all the vectors will go away, the dot products will go away, and we will have transformed that flux integral into just a standard double integral over the xy plane. So good, right? So what is our parameterization?
X, Y, and 4 minus X squared minus Y squared.
He wants x, y, and z is.
4 minus X squared minus Y squared.
Agree? Cool. And what do we need to do? So in order to write this flux integral, what do we need to do?
Take the partial for X and the partial for Y.
Yep. Remember, that's like finding the edges of the parallelogram, right? The Rx is like the one edge, the Ry is like the other edge, and then we're getting the area vector for that little parallelogram. So, and then we're going to do cross product. Here we go. We got time? Yeah. Yeah, we're good. Okay, so we got JK. Partial with respect to x. So we're going to do the cross product. So we're Rx and Ry. Partial with respect to x is 1, 0. You get 2x. Partial with respect to y, 0, 1. You get 2y. So cross product. So I component is it plus 2x? Check, make sure I'm right here. 0 plus 2y and positive 1. Okay, and so then that's going to go here. And then f is, but now f, we need it to what? To be written only in the two variables x and y, right? So this down here is double integral 0 to 1, 0 to 1. F is x, y. Y, what's z? Right, you're going to use your parameters, just like in line integrals, right? Just like in line integrals, use your parameterization to write your field in terms of the variable that you have. In this case, two variables. Remember that? And zx. Dot. Okay, then I think you just have a long but relatively easy double integral in x and y. Is that right? You just do the dot product. So 2x times that, 2y times that, 1 times that. You have an equation of x and y, all polynomial, right? It's all just power rule. Just do lots of power rule. And that's going to give you what? It'll give you the flux of that field through the square part of that paraboloid, which will look something like that. Right, there's the unit square, so it's going to be this paraboloid has a vertex at 4 here. This is 4. So your the surface, so it'll be the flux of that field through that surface. Oh, what's our, let's see. So we talk about orientation. Do x, y. So if you can look at this and you can see what the orientation is. What are values of x and y over that square? Positive or negative or both? It doesn't matter. Doesn't matter. So how did I pick? So this tells us what the direction of the n vector. What's the orientation? How can you tell the orientation is what it is? What's the orientation of that? Right. These are parallel to our n vectors, right? Orthogonal to the surface. So is it up or down, right? So it would be like an up-ish or down-ish. How does this tell us which way it is? The z component, right? For all those vectors, it's 1. That means our orientation is Up. Orthogonal to the plane up. Okay. Take time to watch the video again and pause it and take notes and listen. We just covered lots of stuff.